In the previous lecture, we were discussing an example of mass transfer at an interface where the tangential velocity is non-zero at the interface. Okay. That is the mass diffusion from a gas bubble. You have a constituent in the gas bubble that is diffusing into the liquid around it while the bubble is moving with some velocity. The Peclet number is large, that is the velocity times the radius of the bubble or the diameter of the bubble divided by the diffusion coefficient is large. And we want to find out what is the mass flux as a function of the difference in concentration between the surface of the bubble and the bulk of the liquid. So, this was the configuration that we had selected. You have a bubble of radius r, okay, with a free stream velocity that is incident on the bubble Vfs. Okay. We chose a coordinate system where r is the distance from the center of the bubble, capital R is the radius of the bubble, and theta is the azimuthal angle with respect to the direction of the relative velocity between the bubble and the fluid. And in that coordinate system, the components of the velocity are given as such. Okay. We have defined scaled coordinates, concentration, radius, as well as the two components of the velocity. Close to the surface, you expect there to be a boundary layer where there is a balance between convection and diffusion, boundary layer of thickness delta. In the limit, as the Peclet number becomes large, delta becomes small in such a way that there continues to be a balance between convection and diffusion. So, based upon this, we had got the scaled equation which contained a Peclet number in it. So, on the right side I should note I have d by r square, okay, because I have two derivatives, okay, d by r square. And if I multiply throughout by r square, and if I multiply throughout by r square by d, then I will have on the left side I will have Vfs r by d, okay, which is the same as the Peclet number by 2, where the Peclet number is based upon the free stream velocity and the diameter of the bubble. Okay. So, you have a factor of Pe by 2 on the left side. Substitute r star minus 1 distance from the surface is equal to delta times eta. Eta is a similarity variable which is order 1. Delta is a boundary layer thickness which goes to 0 in the limit as Peclet number goes to infinity in such a way that convection and diffusion are comparable within this boundary layer. Okay. I expand the velocity components Vr and V theta in terms of delta eta. So, for Vr I got it as increasing proportional to delta times eta times cos theta, okay, that is the radial component of the velocity. V theta was actually non-zero at the surface, it was sin theta by 2, V theta was non-zero at the surface. Okay. And over here I have already scaled it. So, I should write this as 1 and I should write on the left side as Pe by 2. Okay. On the left side I should write this as Peclet number divided by 2. Okay. Substituted and I got an equation of this form, okay, and I got an equation of this form. Okay. One part is the concentration field in terms of eta. Okay. One part is the concentration field in terms of eta, the other is delta in terms of theta. For a similarity solution, that first blue part has to be a constant. It can be any constant. Okay. The concentration field in terms of eta will depend on that constant, delta in terms of theta will depend on that constant, but the original concentration field in terms of original variables r and theta will not depend on this constant. So, we can take that constant to 1 without loss of generality. Okay. So, first we solved the red part of the equation, okay, and we got C star in this form. Okay. E power minus eta prime square by 2 d eta integrated. Okay. In contrast to e power minus eta cubed by 3 for a no slip condition. Okay. So this is different because we have a mobile interface. And then we were solving the equation for theta. Okay. So the original equation that I had was Peclet number by 2 into this whole thing is equal to 1. Okay. That is this blue term here. Okay. This blue term has to be equal to 1. Okay. So therefore I divided throughout by 2, multiplied throughout by 2 by PE, and I got this as 2 by the Peclet number. Okay. And then I reduced it to the factor to the form of an integrating factor, and finally I get this expression. Okay. I get this expression for delta square. Let me write it again. Okay. Delta star square is equal to constant by sine power 4 theta plus 1 by sine power 4 theta integral 0 to theta d theta prime of 8 sine cubed theta by the Peclet number. Okay. Okay. And you can use an identity that sine cubed theta is equal to 1 by 4 into 3 sine theta minus sine of 3 theta, okay, to get a solution for this. Okay. So therefore I will not go through the solution, okay, but the the boundary layer thickness, as I said, okay, is a function of the theta coordinate. Okay. At the upstream stagnation point, the flow is incident on the bubble. Therefore, you would expect the boundary layer thickness to be finite. Okay. So the constant C has to be chosen such that the boundary layer thickness is finite at the upstream stagnation point, theta equal to 0. Downstream stagnation point, you cannot enforce that the boundary layer thickness is finite. In fact, it turns out to be infinite at the downstream stagnation point. Okay. Therefore, the constant C that satisfies the condition that the boundary layer thickness is finite at the upstream stagnation point essentially gives us a solution for delta. Okay, delta star is equal to root of 2 by Peclet number, okay, into 8 by 3 minus 3 cos theta plus cos of 3 theta by 3 whole power half. That is the solution you get by the integration and selecting the constant, so that the boundary layer thickness theta is finite at theta equal to 0. Okay, at theta equal to 0, the boundary layer thickness has to be finite. Okay, so that is the constant that you get. Okay. Okay. I am sorry, there should be, let me just correct that, 1 by sine square theta, okay, into root of 2 by PE is equal to delta star. Okay, 1 by sine square theta into this. You can see that the numerator here, okay, this term goes to 0 at theta equal to 0, 1 over sine square theta goes to 0 at theta equal to 0 in such a way that the ratio is finite at theta equal to 0. Okay. So now we have got the boundary layer thickness. In this case it scales as Peclet number to the minus half. For the flow past a rigid surface, it scaled as PE power minus 1/3. In this case, it scales as PE power minus half. You can calculate the flux. Jr at r is equal to r, okay, is equal to minus d partial c by partial r at r is equal to r minus d into Cs minus C infinity by r, okay, partial C star by partial r star at r star is equal to 1, scaling the expression for the flux by r, okay, into 1 over delta star d C star by d eta at r star is equal to 1. Okay. And this d C star by d eta at r star is equal to 1. Okay, we have already calculated that, okay, that was W, okay, in the expression for the velocity field. W was equal to C1 e power minus eta square by 2. W is equal to C1 dt star by dc star by d eta is C1 at eta equal to 0, and C1 was minus root of 2 by pi. Okay. So, therefore, I get minus d into Cs minus C infinity by r 1 by delta star root of 2 by pi. Okay. That is the flux at the surface. Okay. Average flux, this flux at the surface has to be integrated over the surface area. Okay. So, this is equal to 1 by 4 pi r square integral, okay, 0 to 2 pi d phi integral 0 to pi, okay, r square sin theta d theta times the flux at r is equal to r. Okay. And using the expression that I just derived for you, okay, the flux at r is equal to r. Okay. Okay. Integral 0 to 2 pi is just 2 pi, and then the r square cancels. Okay. So, this, okay. Okay. So, this just gives me a factor of 1 over 2 integral 0 to pi sin theta d theta into Cs minus C infinity into the diffusion coefficient divided by r, okay, root of 2 by pi into 1 over delta star. Okay. The only thing that depends on theta here is delta star, and I have to do that integration of delta star with respect to theta. Okay. And that integration can actually be done analytically. I will not go through the details here, all I will give you is the final result. Okay. So, since delta star went as p e power minus half, the final result is proportional to p e power plus half. Okay. It is d into Cs minus C infinity, okay, by 2 root pi r into p e power plus half into 2 by root 3. Which turns out to be approximately 0.326 d into Cs minus C infinity p e power half, okay, by r. Okay. And the Sherwood number is equal to J average by d Cs minus C infinity divided by the particle diameter, okay, which turns out to be equal to 0.652 p e power plus half. For a mobile interface, the Sherwood number goes as p e power plus half and the boundary layer thickness goes as p e power minus half. Okay. I will briefly talk about extending this for a general flow field. Okay. Recall that we had some surface here on which we had, okay, a boundary layer thickness delta. Radius of curvature of the surface is much larger than delta. Okay. Radius of curvature of the surface is much larger than delta, and we have a non-zero velocity at the surface. Okay. We have a non-zero velocity at the surface, mobile surface. Okay. That means that the surface velocity the velocity at the surface is equal to the some function of x. And then we have the no slip condition dvx by dx plus dvz by dz is equal to 0, okay, where x is the streamwise direction and z is the direction perpendicular cross stream direction. Okay. From this we will get that vz is equal to minus vs of x into z. The governing equation Vx partial c star by partial x plus Vz partial c star by partial z is equal to d partial square c star by partial z square, neglecting streamwise diffusion in comparison to cross stream diffusion. Okay. And recall that we substituted eta is equal to z by delta of x. Okay. And what that implies is that partial t by partial z is equal to dc. I should write that's the concentration star by d eta times 1 by delta. Okay. Partial square c star by partial z square is equal to d square c star by d eta square into 1 by delta square. Okay. Differentiation by chain rule. Okay. And finally, I have a derivative with respect to x. Partial c star by partial x is equal to d c star by d eta into minus eta by delta d delta by dx. Okay. Substituting all of these into the governing equation. Vx is Vs within the boundary layer thickness within the boundary layer, because it varies over length scale large compared to the boundary layer, into minus eta by delta d delta by dx, okay, into dc star by d eta, okay, plus Vz, okay, minus Vs into z is delta eta, okay, 1 by delta dc by d eta, dc by dz is 1 over delta dc by d eta, okay, is equal to d by delta square d square c by d eta square. Okay. And then I multiply throughout by delta square by eta. Delta square by d, okay, multiply throughout by delta square by d. You can see there is a factor of eta in each of these terms. Okay. So, one factor that I will get is going to be equal to minus eta dc star by d eta. Okay. On the right side, d square c star by d eta square. Okay. And the first term here, okay, I have taken the negative sign out. So, I will get, okay, Vs delta d delta by dx, okay, plus delta square dvs by dx, okay, into 1 over d, okay, into 1 over d when I multiply throughout by delta square by d. Okay. I multiply throughout by delta square by d. Okay. You can see that these deltas will cancel out, okay, and I have a 1 over delta here. So, I will get Vs delta d delta by dx plus. So, this is c star in terms of eta, this is delta in terms of x. C star in terms of eta is exactly what we got for the flow past a bubble. Had we done the calculation for the falling film, we would have got exactly the same thing. For any interface with a mobile interface with non-zero tangential velocity at the interface, this equation turns out to be exactly the same. What changes is the dependence of delta on the streamwise direction. Okay. What happened, the dependence of delta on the streamwise direction is what changes. This term in the blue box has to be a constant for a similarity solution. That constant can be set any value. Okay. It will not affect the concentration field in terms of the original variables x and z. It only affects the concentration field in terms of eta. Okay. It does not affect the concentration field in terms of x and z. Okay. Therefore, it can be set without loss of generality to just 1. Okay. So, the equation is 1 over d, okay, into Vs by 2 Vs delta d delta by dx, okay, plus delta square d Vs by dx. This is equal to 1. Okay. I can multiply throughout by d. Okay, I multiply throughout by d to get d on the right side. Okay. And Vs delta d delta by dx, I can write this as, okay, 1 by 2 d delta square by dx. I can write this as 1 by 2 d delta square by dx. Okay. Multiplying throughout by 2 by Vs. Okay. I multiply throughout by 2 by Vs, d delta square by dx plus, okay, 2 delta square by Vs d Vs by dx is equal to 2 d by Vs. This is once again an equation of the form dy by dx plus p of y is equal to p of x into y is equal to q of x. Okay, this is once again of that same form. Integrating factor is equal to e power integral p dx e power integral of p is 2 of dx into, okay, 2 by Vs d Vs by dx. Okay. 1 by Vs d Vs by dx is e power integral of dx into 2 d of log Vs by dx, okay, which is equal to e power integral dx into d of log of Vs square by dx. Okay. It's equal to log e power log of Vs square, which is just Vs square. That is the integrating factor. Okay. Okay. Therefore, delta square will be equal to constant by Vs square plus 1 by Vs square integral 0 to x dx prime, okay, 2 d by Vs into Vs square. Which is equal to c by Vs square plus d by Vs square integral 0 to x dx prime, okay, this factor of 2 here, dx prime times Vs. Okay, so, that is the expression for the boundary layer thickness. Okay. And this is the the constant C has to be determined from the condition that the boundary layer thickness is 0 at the start of the heating section or at the start of the contacting section. Okay. At x is equal to 0, the start of the contacting section or the start of the heating section, boundary layer thickness has to be equal to 0, which implies that this constant C is equal to 0. Okay. And therefore, we get delta square is equal to 2d by Vs square integral 0 to x dx prime times Vs. Okay. So, if I know what is the Vs as a function of x, right, then I can calculate the boundary layer thickness as a function of x. Okay. I can calculate the boundary layer thickness as a function of x. And once I know the boundary layer thickness, I know that Jz is equal to minus d into C s minus C infinity, okay, sorry, by delta into dC star by d eta at eta is equal to 0, which is equal to d into Cs minus C infinity by delta into root of 2 by pi. Okay. And the average flux is integral of this from 0 to x. Okay. And that is how you can calculate the Nusselt number correlation locally and then integrate over x in order to get the Nusselt number correlation for the average flux. We had solved the problem of a falling film. In that case, Vs was a constant. Okay. For a falling film, okay, Vs is a constant. Okay. Therefore, delta square is going to be equal to 2d by Vs square into integral 0 to x of Vs times x is just going to be equal to Vs times x, okay, which is 2dx by Vs, okay, at the surface. And recall that for that case Vs was equal to 3 by 2 times V average. Okay. So, this is going to be equal to 4 dx by 3 V average. Okay. And from that we get the boundary layer thickness as 4 dx by V average per half. Okay. The boundary layer thickness scaled as x per half in that case. For the flow past a rigid surface, it scaled as x per 1/3. For the flow of a falling film, it scaled as x per half. Okay. And that is the reason it scales as x per half, because the velocity is non-zero at the interface. When the velocity is non-zero, then the convective effects are stronger at the interface, and therefore you get a faster increase in the boundary layer thickness. Velocity is 0, the convective effects are relatively weaker at the interface. Therefore, the increase in velocity with downstream distance goes as x per 1/3. So, this completes our discussion of forced convection. Okay. This completes our discussion of forced convection at high Peclet number. Okay. High Peclet number flows. Limit as Peclet number becomes large, the disturbance to the concentration of velocity field due to a heated or a higher concentration surface is restricted to a thin region close to the surface. Rigid surface with no slip velocity condition, boundary layer thickness where convection and diffusion are comparable goes as P per Peclet number per minus 1/3, the boundary layer thickness. Nusselt number or Sherwood number goes as Peclet number to the plus 1/3. Temperature field in terms of the similarity variable is the same for all configurations. Boundary layer thickness in terms of the streamwise coordinate is different, it depends on configuration. When there is a mobile interface, there is a slip condition at the surface, boundary layer thickness goes as Peclet number to the minus half, and the Sherwood or Nusselt number goes as Peclet number to the plus half. In this case as well, T in terms of concentration in terms of eta is independent of configuration, boundary layer thickness depends upon configuration. So, we will continue our discussion of forced convection in the next lecture.